So lesson 8.3, picks up right down here underneath where we left off yesterday. And we're going to be talking about some various characteristics of graphs, specifically vertical asymptotes, horizontal asymptotes, and holes. And so we're going to look at how to find those, talk about what they mean. And then we're also going to, I believe the homework also talks about domain and x and y intercepts. So we're going to look at those too. On this side, I'm going to run through all the definitions, try and explain it. And then on the back side, we'll probably do about 2 examples. By the time I explain everything and go through the details, that would be my expectation there. So, first things listed here, vertical asymptotes. We talked about vertical asymptotes, yesterday. Yes? Okay, we talked about them yesterday. And when we had our vertical asymptotes, first of all, one thing to note is it was always x equals a number, right? When you do an equation for a vertical asymptote, it is x equals a number. So vertical asymptotes, always x equals a number. And how do we find vertical asymptotes when given an equation? And notice it says, found by setting the denominator equal to 0. So as you look at some of these equations we're going to do, it's no longer just, 12 over x. There's more pieces to it than that. And so when we go to look for vertical asymptotes, we're going to set the denominator equal to 0. If you use, do you see that little example right there? If you use that example right there, what would be the denominator we'd be setting equal to 0? We would set 3x minus 1 equal to 0, and I'm just going to do that off to the side here. If it's 3x minus 1 equals 0, how do we solve that? Okay, we're going to add 1. So 3x equals 1, and then we're going to divide by 3, and x is 1/3. That is an example of a vertical asymptote. Okay, so it's always just taking any factors in the denominator and setting it equal to 0. So I just wanted to show you an example there. Horizontal asymptotes. We looked at horizontal asymptotes yesterday. Pause, rewind, insert. Vertical asymptotes. Forgot one thing about them. Okay, vertical asymptotes. You guys know yesterday we were drawing them there, those dotted lines we draw in that technically are invisible, but we draw them in, right? Okay, so because it's an asymptote, when I'm drawing the graph, okay, so like if I have a curve on one side, in order to draw the curve on the other side, I have to pick up my writing utensil, yes, move it over, and then draw the curve on the other graph. So because my graph has a break in it, it is what we call discontinuous. In other words, it's not continuous. A graph can either be continuous, where you're constantly drawing, there's no breaks, no gaps, or it can be discontinuous. And a vertical asymptote makes a graph discontinuous because there's a break. You have to pick up your writing utensil and, go from there. So what I want to talk about is a vertical asymptote is a point of discontinuity. Specifically, it's a non-removable point of discontinuity. So if you're asked what type of discontinuity it is, anytime we talk about a vertical asymptote, it is a non-removable point of discontinuity. So I'm going to write that in right here underneath vertical asymptote, that it is a point of discontinuity. That was me spelling it as I went. Okay, it's a point of discontinuity, specifically non-removable. Non-removable, I like to think it's non-fixable. An asymptote, there's a big break in the graph. It's not like you can just put it back together. It's non-removable. I'll let you get that written down. And now I'm ready to talk about horizontal asymptotes. So horizontal asymptotes, we talked about those yesterday as well, right? Horizontal asymptotes, if you recall from yesterday, were always y equals a number. And notice here what it says. Read that. If you read that first sentence, it says, found by analyzing the biggest powers on top and bottom. Okay, so meaning you're looking at the highest exponent, highest bottom, and then you decide what to do from there. So the next one says y equals the ratio of the coefficients of the biggest powers if the biggest powers on top and bottom match. So if your highest power on top, your highest power are the same, then we take the coefficients, the numbers out front. And lastly, there's no horizontal asymptotes if the biggest power is on top. Now, if we use our example up top, right here, to talk about biggest powers being on top or bottom, okay, what is my biggest power on top in the numerator? 3. And I'm going to write the whole term down in that it's 3x to the third, right? That is the largest powered term. What is the largest power in the denominator? 3x, which the invisible power there is 1. Where is my bigger power? On top, yes? What does it say over here? If the bigger power is on top, there's no horizontal asymptotes. So this particular example right here would have no horizontal asymptotes because 3 is the bigger power and is on top. What if the bigger power, what if that 3 was on bottom? What if this fraction was upside down? It'd be y equals 0. What if these powers match? What if they were both 3x squared? The ratio of the coefficients. What are the coefficients of these terms? These whole number 3's outside, or out front. And what is 3 over 3? 1. Okay, so those are your different options, and we'll practice some with those, but those are your different options of what can happen with horizontal asymptotes. Okay? Questions there? Okay. The other thing we're going to talk about are holes. So a graph can have vertical asymptotes, so like a vertical line break. It can have horizontal asymptotes, if our graph might run along, or it can have a hole. So for an example, there's a graph with a hole. What is it basically? A little tiny break. Okay, that's an example. If you're talking, what do you mean a hole, Mrs. Sargent? It's just like one little point where the graph doesn't exist. Now, in all honesty, what do we often do to show it? We often put like an open circle to show it. But the idea is it's just one small break in the graph. That is a hole. Now, similar holes kind of go along with the vertical asymptotes. A hole is always x equals a number. And a hole occurs if the functions on top and bottom can factor and reduce. The hole is the answer to the canceled piece. So basically, if you have a factor on top that cancels with a factor on bottom, that indicates there's a hole. Okay? We'll have an example that has a hole there. Now, a vertical asymptote was a break in a graph, right? It was a point of discontinuity, non-removable. Guess what? A hole is also a break in the graph, right? It's a point of discontinuity, but it is removable. So I'm going to write that down. Point of discontinuity. I'll save you from my spreading it out as I'm trying to spell it. And this one is removable. I think about a hole. You could like remove the plug, put the plug back in. I don't know. You have to come up with your own way to remember them, but Now, mostly this lesson focuses on two types of asymptotes and wholes. However, I believe in homework it also talks a little bit about domain and x and y intercepts. So before I flip over, this way you can have all your information together. How did domain look yesterday? It wasn't just x equals though, it was all reals except x equals something, right? And that x equals something was always also our vertical asymptote. Okay, so our domain today is going to be all reals except any vertical asymptotes and any wholes because they're also x values. So domain, all reals except wholes and vertical asymptotes. Now, while we're here, let me share some information about x-intercepts and y-intercepts. An x-intercept is when we cross the x-axis, right? That happens when y is 0, which happens when your fraction is 0, which, okay, the shortcut in order to find x-intercepts, set your numerator equal to 0. So instead of denominator equal to 0, it's going to be numerator equal to 0. So x-intercepts happen when y is 0, so it happens when the numerator is 0. Y-intercepts, they just happen when x is 0. So with a y-intercept, we're just going to let x equal 0. So we're just going to put 0 in for x. Excuse me. Okay. Get what you need there, and then I am ready to turn to the next page. Huh? What, yawn? Sorry. Let's just say I'm ready for the weekend. It has been a busy week. And last week was it's like been a busy 2 weeks. It was a busy weekend and next Thursday at 3 o'clock, right? We're all looking forward to it. I could go with that. But honestly, my weekend's not as busy as my last couple of weeks has been. So I light at the end of the tunnel day today. I'll take something, anything to get me to spring break right now. Okay, so on the back side, there are a lot of examples. To be honest, we're probably going to get through about 2 by the time I talk about everything. Okay, and it's not that these types of problems take that long on their own. It's just me explaining everything. Okay, so you will notice it's asking us to identify all horizontal asymptotes, vertical asymptotes, and wholes for each function. I'm also going to throw in domain and x and y intercepts because the homework asks you to do that, right? So I want to prepare you. Did you see the comment here? Go in this order. And they suggest that we do wholes, then vertical asymptotes, then horizontal asymptotes. Here's what I'm going to say. It is important that we check for wholes before we check for vertical asymptotes. That is an important thing to do. Horizontal asymptotes could be before or after. It honestly doesn't matter. But the fact that we do wholes and then vertical asymptotes is important. Okay? Now, we're going to work on A. I'm going to be honest with you and tell you we're not doing B because I'm going to write in A and B spots. Okay? And before we jump into A, well, we are going to jump into A, but before we get thoroughly started on A, we need to factor this. In order to think about setting denominators equal to 0 and whatnot, any of these you work with need to be in factored form. Do you remember how to factor? We've got to know how to factor, okay, guys? So when I talk about factoring this, First of all, the numerator of x plus 3, does that factor? X plus 3 is already a linear factor. It's just x to the first, so it's good. Okay, dig deep. X squared minus 4x plus 3. It factors. I promise you it does.
That multiplies the 3 to add up to 4. So it would be 3 and 1.
Okay, it's coming back. I'm hearing bits and pieces. I just wrote the 2 parentheses as a hint. If you're still sitting there saying, what are we talking about? Do you hear some people talking about multiply to be something, add to be something else? Yeah, that's what we're talking about here. Multiplies to be the 3 at the end. So product of 3 adds to be the middle number of negative 4. Does this ring some bells? You've done this in Algebra 1. We've done this in Algebra 2. It's not new. What multiplies to be 3 and adds to be negative 4? Okay. 1 times 3 is 3. If it multiplies to be positive, they're the same sign. If it adds to be negative, they are both negatives. What did I not put at the beginning of these parentheses yet? X's, right? X squared breaks into x times x. Okay, this comes back to you, right? Okay. Now, with that in mind, it said holes. And you have that chart on the previous page, right? And if you read about holes, it says they occur if the functions on top and bottom can factor and reduce. So you're looking for any identical factors that would cancel. In the denominator, I have an x minus 1. Do I have an x minus 1 on top? No. In the denominator, I have an x minus 3. Do I have an x minus 3 on top? No. On top, I have an x plus 3. Is there an x plus 3 on bottom? So can anything cancel? Nothing can cancel, so guess what? No holes. None. And I'm going to write an explanation there. No factors cancel. So if you're using this as an example to help you with homework and you want to see why we put none or no, it's because there was no factors to cancel. Okay, are we good with holes on this one? We'll get to one that has holes, I promise, okay? So next, vertical asymptote. And we have to do holes first because there can't be holes and vertical asymptotes at the same place. So, okay, how do we do vertical asymptote? It said to what? Denominator equal to 0. What do I have in my denominator? X minus 1 and x minus 3. So what are we going to set equal to 0? X minus 1 and x minus 3. However many factors in the denominator, you set equal to 0. How do we solve those? You add 1 on the one, add 3 on the other, right? So what are my vertical asymptotes? So vertical asymptotes, x equals 1, x equals 3. Are we okay with that? Now, before I continue, what type of points of discontinuity do we have at 1 and 3? Because these are vertical asymptotes, they're discontinuous. What type of points of discontinuity are there? What's the word? Non-removable. Okay, so and again, in case they ask anything about that in homework, I'm trying to prepare you that these right here are points of discontinuity, and specifically they are non-removable points. So the key is if they ask you what they are and they're vertical asymptotes, non-removable. Got it? Okay. Holes. It's off the screen. You guys got to tell me when I do that stuff. Holes, vertical asymptote, and now horizontal asymptote. Okay, flip back. What's it say about horizontal asymptotes? There's a whole big paragraph, but found by analyzing the biggest powers on top and bottom. Now, go before you factor. Go for when it's all multiplied out and not factored. What is the biggest power on top? On top, we have an x to the first. In the denominator, before we factored it out, what was the biggest power in the denominator? X squared. So if we have x to the first over x squared, where is the biggest power? On bottom. What does the rule say? If the biggest power is on bottom, what is the horizontal asymptote? Y equals 0. And why did I say y equals 0? Because the biggest power was on bottom. Okay, remember I still want to talk about domain, x and y intercepts. In all honesty, we got the harder part out of the way, though, if you ask me. Domain.
All reals except those 2 points.
Okay. Domain is all reals except any holes or vertical asymptotes. What did we have? 2 vertical asymptotes, right? So all reals except x equals 1 and x equals 3. Okay, x-intercept. What did it say? Or what did I say earlier? Sets any numerators equal to 0. What's in the numerator? X plus 3. So if I set x plus 3 equal to 0, and you solve, you're going to get x equals negative 3. And lastly, y-intercept. How do we find a y-intercept? A y-intercept is going to happen when x equals 0. That says let x equal 0. My let and x kind of went together, but I promise that's what it says. So that means you go back to either your original equation or your factored equation and put 0 in for x. So your choice, which you use, if I use my original, instead of x plus 3, I'm going to say 0 plus 3. 0 squared minus 4 times 0 plus 3. If you'd prefer to use the factored version, you're just putting in 0 for each of the x's. 0 plus 3 is 3. 0 squared minus 4 times 0 plus 3 is 3. What is 3 over 3? 1. So my y-intercept is 1, or in other words, y equals 1. Okay. My plan is to try and go through C now. Huh? Okay. Before we get started, I'm going to suggest that we do any factoring you can. I mean, you don't have to factor first step, but you're going to have to factor, well, as soon as we start talking about wholes. So yeah, basically first step. Okay, does anything factor here? We're hoping that numerator factors. X squared breaks into x and x, two numbers that multiply to be -4 and add to be -3. Say it's some combination of 1 and 4, +1, -4. And my denominator of x minus 4 is just going to stay. If you guys are caught up, I will zoom in here a little bit. Okay, wholes occur if the function on top and bottom can factor and reduce. The whole is the answer to the canceled piece. Do I have any identical factors this time? Yeah, I told you I'd show you a whole, right? Okay, here we go. X minus 4 is in common, so it can cancel out, which means there's a whole at x minus 4. Now, if you set x minus 4 equal to 0, what does that give you? X equals 4. So basically, you take that canceled factor set equal to 0. So there is a whole at x equals 4. And why did we pick x equals 4? Because the x minus 4 cancels. And then we set x minus 4 equal to 0. And once we set x minus 4 equal to 0, it gets x equals 4. Whatever explanation sound you need to write down. No. Nope, I'll be writing into D. What type of discontinuity is this? A whole is what type of discontinuity? Removable. So this x equals 4 is a point of discontinuity. It's a break in the graph. And because it's a whole, it is removable. Again, just trying to help you prepare here and think about this stuff. Okay, we've already talked wholes, yes? Next, we're going to talk vertical asymptotes. How do I decide vertical asymptotes? Set the denominator equal to 0. What happened with our denominator, though? It canceled to become a whole. A point could have a whole or a vertical asymptote, but you can't have a whole and a vertical asymptote at 4. It's not possible. It's one or the other. Do we have any other factors that could give us vertical asymptotes? No, our only denominator was x minus 4. And since x minus 4 ended up showing a whole, then vertical asymptotes? None. Okay. If you want an explanation, there was a whole at x equals 4, and it could be a whole or vertical asymptote, not to both. Feel free to write yourself notes. Horizontal asymptote when you're ready. How do we find horizontal asymptotes? Powers. Before I factored this, what was my biggest power on top? X squared. What was my biggest power on bottom? X to the first. Where is my biggest power? On top. Read the rules. Biggest power on top says no asymptotes. And again, my reasoning was bigger power on top. Okay. Domain and intercepts to finish us off. Domain. These graphs are going to extend infinitely in both directions. So like yesterday, it's all reals except x equals 4 because 4 was a hole. Any holes are vertical asymptotes. Those are breaks in the graph. So those are going to be exceptions for my domain. So all reals except x equals 4. X-intercept. Set the top equal to 0. Now, okay, the factored top. What is in our numerator? Okay. It was x plus 1 and x minus 4, yes? What is happening at x minus 4? There's a hole. So if there's a hole at x minus 4, there's a break in the graph. Can that also be an x-intercept? Does my graph technically touch the x-axis there? No. So because that canceled, we won't worry about it, and we will just use x plus 1. So if you set x plus 1 equal to 0, where am I going to have an x-intercept? Yeah. Whoops. X plus 1 equals 0, so x equals negative 1. And lastly, y-intercept. How do I do a y-intercept? Yeah. Let x equal 0. Use your factored. Use your original. Actually, it'd be really easy to use the factored here. Because if you use the factor, you're just putting it into x plus 1, okay? If you'd rather go back to the original, then fine. It's 0 squared minus 3 times 0 minus 4 over 0 minus 4. End up with negative 4 over negative 4, which is 1. So y-intercept of 1. Okay, guys. Your homework is to do 8.3 for Monday. Okay? Monday we will definitely have some time to talk about questions if we need to and figure out what's going on, you know, if there's any questions. I've tried to show you a little bit of everything here. I mean, I guess there's one type of horizontal asymptote we didn't get to talk about, you know, so we can pick up with questions on Monday if we need to, but do lesson 8.3 for Monday.
I was about to ask.